Hi guys, so today we're going to do this Atcoder beginner contest 199. So this is actually rated for me. Uh, so we'll talk when once this is done, and we'll be discussing the solutions then. Okay, that was just simple implementation. Let's see this one. Okay, greater than max A and smaller than min B. Okay, so we will do the flip query lazily, I guess. Okay, so just changing whether it is flipped or not. Okay, thing is 2L, right? Okay. Let's flip. We want different indices. Okay. And let's do. Simple and directed graph with vertices images. Mhm. Okay. Tripartition, I guess. Okay. Exponential will work. Mm, I think we can try everything because that's 3 to part 20. That's slow. Awesome. Okay. Okay, we can take it down to 2 to power 20. Uh, just put a different color than the parent. Or for each connected component separately. Okay, so backtracking kind of. Yeah, so definitely wasted a lot of time there. Will be penalized for that in the rank list. But yeah, anyway. So in this one, I think there are a lot of constraints here. We have to satisfy all of them. Okay, find the number of permutations that satisfy these things. Okay. Okay, so I think they all give us a prefix. Yeah, okay. Each of them is giving us a prefix. Then what is it? Okay, prefix. For each prefix we have these many numbers as well. This. Yeah, okay, so it's a decreasing kind of thing. So like if y increases, z has to either decrease or stay the same. That goes for each prefix. I think there's some relationship there as well. Yeah, I think it can only increase by 1. Okay. Okay, so if only these many numbers are smaller or equal to yi, then if we add another element, that is also smaller or equal to the 1, but that's it, right? Mhm. Two. Okay, so we get instant. Mhm. Okay. If till x plus 1 we have these many, do not have more than that. Till 8 and x we have up to 5 number. 9, 9 x we got almost 7 and x will be on this one. The constant will go backwards, so you get 10, not have more than 8. For every prefix we have at most how many numbers we can put in the beginning. Mask DP maybe. Uh, Okay, could be TLE, but let's see. Okay, it worked. Worked really fast. Okay. Last one left, and how much time have we spent? I think a lot of people must have finished the content by now. Yeah, a lot. 76, I guess. Okay, 45 minutes, 46 minutes have been spent already. I hope this is simple. Wow, this looks interesting. Hmm. Okay, just model arithmetic. Um, I don't really get what this. Okay, expected value. Okay, I think each edge is. Just a second. Okay, we're choosing edges. With the graph. And K is very big, but N is small. Okay. And M is full, I guess. N is small. What will happen after K operation? I think the sum of everything should stay the same. 5, 8, 14, 2, okay. Is it like part thing or is it? Oh, part thing. Mm, mm, yeah, part kind of thing. Well, Oh, wow, all this work. Constants look like something matrix. Okay, maybe we can model one once operation using matrix multiplication, and then we just raise it to the power or something. Okay, but how? How can we model it? Yeah, take the open again. Okay, we divide by m at the end, right? And we sum up everything. Now, for each edge, we had the answer for these three edges, and we just add it itself for everything else and divided by m, I guess. Hmm. But I don't know how many adds itself to depends on the number. M. Okay. Edge can be part of changes to vertices. Mostly self by 2 plus. Hmm. Okay. Okay. What was all the knowledge? Okay, it wants the sum of everything. 1/2 n time, right? Everything that is existent itself. N minus t by 2n plus 1/2. 2n minus t by 2. Okay. Mm. Four minus 2 by 4. Okay, good. Matrix multiplication then. Right. Okay. This is the answer vector again. Degree. Okay. We also need the answer vector. Wait a second. Okay, yeah, it's probably right. I don't know what can go wrong there. Okay, done. Right, so let's see what's the final rank. I don't think I have any penalties, right? So whatever the rank is, final rank now. Because this also has, Atcoder also has the uh, kickstart kind of rank list. So like, yeah, so like if you have 77th rank when the contest ends, like it won't change. If you have no penalties, it won't change. Okay. Too many Japanese people above me, like almost everyone is Japanese. But then this is a Japanese website anyway. So yeah. Anyway, so let's talk about the solutions now. Okay, let me see if I'm audible. Hello, hello. Okay, yeah. So this one was pretty trivial. Just like it's just given you have to print yes or no depending upon this condition is true or not. So yeah, just like this is simply nothing. Just code. Okay, yeah. So it's simply nothing. Just actually do it and check if it is true. Then print yes, otherwise print no. Yeah, that was nothing. Then we have the second problem. Okay, yeah. So this is kind of a range that is imposed on this x. Now we want to find the number of x that satisfy these conditions, all of these conditions, right? So we see that x has to be greater than all of the ai, and x has to be smaller or equal to all of the bi, right? That means x is greater or equal to the biggest ai, and also x is smaller or equal to the smallest bi. So I just found the maximum of a and the minimum of b. That's all we need, and we want to find all of the numbers that are present between this range, from max a to min b, and that is min b minus max a plus 1 if this value is smaller than 0, which could be possible if like some b is smaller than some a. So in case we just print, in that case we just print 0, right? So it will be more clear when I show you my code, right? So instead of actually taking the arrays, I just take two variables a and b, and in a I'm storing all the minimum for all a's, and in b I'm storing the maximum of all b's. Okay, so right, so in a I'm storing the maximum of all the values of the first array, and in b I'm storing all the values, all the minimum of all the values from the second array. And yeah, so I print b minus a plus 1, but if that is smaller than 0, then I print 0 instead, right? So yeah, that's it. Then we have this problem C. Yeah, okay, so this was also an implementation kind of problem. In fact, if this second operation was not there, it would be too trivial. You just have to swap two characters when it asked you to do that in the input, right? So basically, even with this operation, it's still almost that only. It's just that if you actually perform this operation of swapping, so if you actually perform it, it can go a little bad, because like n is too big. So if you actually swap them, then too much time will be taken in doing that. So to make sure that like we don't TLE, what we can do is we can perform this second operation lazily. So by lazily, I mean that we won't actually perform it. We will just remember whether this operation has to be performed in the end or not, right? So when we remember whether we have to flip it or not, then we also have this first operation. So like based on whether we have to flip it or not. So basically, if we have to flip it twice, that means we don't have to flip it at all. So based on our memory about whether we have to flip it or not, um, we can kind of get the new indices that we have to swap based on the AI and BI. And yeah, at the end, if the lazy is true, then you just actually swap it once, and that's it. So this works in linear time. Okay, right. So this was my code. Okay, okay. Right. So I have a variable, Boolean variable named flip, which is true if I have to swap the two intervals once. And yeah, so whenever t equals 2, I just toggle this flip variable. So like if it is true, I make it false. If it is false, I make it true. And yeah, so if I don't have to flip, I just swap the ath and bth character. But if the flip is true, then I change the a and b accordingly. That is, add or subtract n to it, and then do the same thing again. So yeah, that's it. After that, in the end, if the flip is true, I swap the two ranges. Otherwise, I don't. Now we have this problem, RGB coloring 2. Yeah, okay. So this is basically like kind of like a tripartition. So this is actually an NP complete problem, tripartition. But since n is not very big, so we can actually come up with some kind of exponential solution here. And what one would initially think for this problem is you have three sets, so you can kind of put each vertex in one of the sets and then check whether it is valid or not, and then add all of the sets, right? So the problem with that is you can have up to 3 to power 20 sets, which is like too much. So obviously you cannot run 3 to power 20 operations in a given time bound. Moreover, each check operation will work in O of m time, so that will be even slower. But yeah, so we cannot do it. But one thing we can notice is that if we have multiple connected components in the given graph, then we can solve for each of them separately, right? So we have to solve only for a single connected component, and for each connected component we have to solve separately. So the thing is, it is easier to solve within a given connected component, because like if we put a certain value at any point, the values that we can put on the vertices that are adjacent to it are not three, they are just two. So for example, if I put the first vertex as red, then the all the vertices that are adjacent to it can only be green or blue, so they cannot be red, right? So instead of having three options at each point, we only have two options at each point, which makes the algorithm 2 to power 20 instead of 3 to power 20. So basically, like we get a 2 to power 20 algorithm which can just work with backtracking. So like what I did in this problem was I just made a DFS tree, got a little stuck at the implementation during the contest. But yeah, so basically what we had to do is we had to make a DFS tree. I think if I had it made it explicitly and then solved it later, then it could have been a little easier. But yeah, so there was some issues with that. But anyway, so once you make a DFS tree, for that I just mark the level, and like if the adjacent vertices level is one more than the current vertices current vertices level, then that means it is a child in the DFS tree, right? So that's what I use to identify which edges belong to the DFS tree and which don't. An easier thing could be to first make the DFS tree and then solve accordingly, right? So DFS tree is nothing but just when you perform a DFS, then all of the edges that are actually used, they form a tree, and that tree you can call it a DFS tree. Yeah. So basically, you first make that tree, and after that perform simple backtracking. Like if a certain vertex is red, you can try all other colors in the children, right? So for each vertex, there are only two options now instead of having three options. So your recursion tree grows just to 2 to the power 20 instead of 3 to the power 20, right? So yeah, that works in the given times, and you just have to multiply the answer for each connected component. So that's what I did here, and yeah. Okay. So now we are at problem E, which was also kind of simple. I wasted a little time here, but yeah, it wasn't difficult. It was actually simple. So we want to print the number of sequences that permutations of a given this thing, like we want to print the number of permutations which satisfy the following conditions, right? So the conditions are something like, so it is given like you are given m conditions, and in each condition you are given a prefix of the permutation, and you want that in that prefix the number of elements that are smaller or equal to the given y are at most z, right? So you are given a lot of conditions, like these three numbers x, y, and z. So basically in the prefix of length x, you want the number of elements that are less than or equal to y to be less than or equal to z, right? So that's what you want. You want to satisfy all of these conditions. So I was trying to come up with some kind of greedy solution using these conditions, and that's what I was doing wrong. It is like a straightforward DP. So what we have to do is we have to make a bit mask DP. So we have to keep a mask of all the elements that we have already used, and the elements that we haven't used yet, that those we can use now. So basically, since we will only use each element once, it will automatically be a permutation, right? So we need a bit mask of length n, which is like 2 to power n, and then we also need to remember the position that we're on. So that gives us n into 2 to power n, and then we will also iterate on the element that we will be putting at that point. So that gives us a total of n square into the bit mask, right? And at each position we have to kind of also check whether any of these condition fails or not. So if any condition fails, then we can just directly return 0 there, right? So yeah, I just did some recursive DP here. I think iterative could also have been done, but I initially thought of recursive, so I just went on with it, right? So for each that's how I'm storing these conditions. Like for each x in a vector, I'm storing the pair of y comma z, so that I can easily find it when I want it. And in my recursive DP, I have the position and the mask. Okay, and yeah, so I first of all I check for all conditions, all the given conditions. I take the y and z, and I check whether any of the condition is being violated or not. So if any condition is being violated, I just return 0 there, and yeah, so that's it. And the way I am checking whether a condition is holding or not has a lot to do with bit manipulation and everything. I think you can pass the test cases even without doing all this. You can maybe simply make a vector and put everything there, so maybe that will also work. But yeah, so basically here I'm doing some bit manipulation kind of thing. So when I take modulo with 2 to power y, what this does is it only leaves the elements that are smaller than y in the bit mask, right? And then I do the built-in pop count of all that, so I get the number of elements that are smaller or equal to y. And yeah, so if that count is greater than z, then the condition is being violated, and I return 0 there. Otherwise, yeah, so basically I try to put each element that hasn't already been used at that position, and I add all of the answers and just return it. Yeah, that's all we have to do here. This actually is kind of a standard technique to use bit masks to make permutations with given constraints, right? So if you are given some constraints and you want the permutations to satisfy the said constraint, you can do something like bit mask DP, right? So it is kind of like a standard technique. Okay, finally we are at this F problem, which uses matrix exponentiation as a prerequisite. Right, so I'll be putting the link to my course on matrix exponentiation in the description, right? So I taught a class on that. That is the prerequisite to this. So if you want to solve this problem, you need to know how matrix multiplication can help us solve some special problems, and yeah, so things like that. Okay, so now let's try to examine this problem. We are given a simple graph, and by a simple unrelated graph it means that so by a simple graph it means that there are no self loops or multiple edges, so that will be helpful later. And right, so each edge has right, so there are a lot of edges, and each vertex has a number written on it. Okay, and you will do the given operation k times. Okay, so k can also be 0, by the way, and you will do the given operation k times. So what we will do is we will choose one from the m edges uniformly at random, and from other, okay, independently from other choices, right? So for like at each step we just randomly choose an edge, and we want the arithmetic mean uh, on the numbers, like the two vertices that are connected by the edge. We want the arithmetic mean of those numbers, and we want to replace each of the number written there with the value x that we just found, that is the arithmetic mean. Okay, so something like, they don't have a diagram. Yes, basically, like here you can see 1 and 2 are joined and the values are 1 and 3. So if you perform an operation on this edge, instead of 1 and 3, both of them become 2 and 2, right? So yeah, something like that is happening here. And okay, so first of all, if k equals 0, then the answer will just be the input array, that is this thing. Okay, maybe there is a case with k equals 0 in the sample. Okay, there's no such case. But yeah, it is kind of easy to see that if no operations are happening, then none of the values will change. So yeah, it will remain the same. And this array itself will be the answer. But if k is not 0, let's see what will happen if k is equal to 1. So if k equals 1, then there are a lot of operations that can happen, and we can take the average of the value of a vertex depending upon each operation, and that will be the expected value of that vertex, right? But what will we do for multiple operations, right? So what if k is greater than uh, a second. Okay, so what if k is greater than 1? Okay, so we can break this due to linearity of expectation and all that. We can break this into multiple steps, which means first we like if k equals 2, like let's take the general case, let's take the very specific case k equals 2. So for that, what we can do is take the input vector, take the input vector a, and run it through our code twice. Okay, so basically k equals 2 is same as doing k equals 1 2 times, right? Because this is basically because of the linearity of expectation. We will take the expected value of all of the vertices after one move, and then we will take their average in the second move, right? So yeah, that's basically it. So what we want to do is we want to perform k moves. It is the same as performing one move k times, right? So performing k moves is same as one move k times. Okay, so yeah, so performing k moves is same as performing one moves like one move k times, right? So we need to be able to do all of this quickly, right? So that's where matrix multiplication comes in. We will use matrix multiplication to actually do this one time, and to do it k times we will raise the matrix to the power k and then just multiply it once and we'll be done. Okay, yeah, so we'll be going to use we'll be using matrix multiplication for this. Okay, and yeah, what are x and y? Okay, these are the edges, right? So we need to examine our matrix, right? So for that we need to examine what one move will look like. Okay, so at the end of one move we will like basically multiply 1 by m, because that is the probability that we take a certain edge, right? So we multiply the sum, that sum of values that we will get if we choose a certain edge at a given vertex, and then multiply all of it with 1 by m, right? So it is something like we take 1 by m and multiply it with the answer that we will get, like so, like the summation of like for each edge we choose, we want the value of a given vertex. Okay, so it is something like new AI equals summation of for each edge we take the value of AI. Okay, new value of AI for each edge chosen. Okay, and we kind of know that if the edge that is chosen is not the is not linked to the vertex I, then the value won't change, right? So it will stay the same if the edge is not adjacent to this. But if it is adjacent to it, then we just have to add something like let's say there's an edge between I and j. We will take something like AI plus AJ by 2. Something like this we will add. And this means that for each edge, since we have to add this for each edge, that means it will become something like so this will be equal to d, which is the degree. Okay, so degree times AI plus the summation of AJ. Okay. So we want the summation of all the so we want summation of all the vertices that are adjacent to the vertex I. Okay, and we divide it by 2, and lastly we divide it by m. We basically divide it by 2m. Okay, so this happens if we take an edge that is actually adjacent to the vertex I. But what if we take an edge that is not adjacent to the vertex I? So there we have m minus d such options. Okay, so we have m minus d such options, and okay, we'll divide it by m at the end. And for each such option, the answer will remain AI. Okay, so yeah, so if we actually add all of this up, we get something like so yeah, this becomes 2m, this becomes 2m minus 2d. Okay, and when we actually add this, we get AI into 2m minus d by 2m plus the summation of AJ by 2m. Okay, right? So yeah, so this gives us a matrix, and the matrix is simple. So basically this AJ and AI etc, everything will form a column vector which we will just multiply, and the square matrix will just be the adjacency matrix with diagonal elements same as, so our matrix will be like matrix I comma I will be nothing but 2m minus di by 2m. Okay, because when we multiply it, this gets multiplied with AI and gets added to our answer like this. And for any other matrix ij, it is equal to 0 if no edge is there between I and j. If no edge between I and j. Okay, otherwise if there is an edge, then matrix of ij will be equal to just 1 by 2m. Okay, yeah, and basically that's all I did in this problem. And when we have this matrix, we just have to do something like matrix to power k multiplied by the column vector, that is a, and yeah, so this gives us our answer. So yeah, that's all we had to do here. Let me show you my code also. Okay, so obviously you won't understand anything about this if you don't know matrix multiplication. So as I said, I'll be putting the link to the lecture I did on this, so you can watch it. But yeah, so this is my code for matrix multiplication. This is like a pre-written structure which quickly performs matrix multiplication and binary exponentiation of matrices. Anyway, so Yeah, so this is the main part. I have a variable in which I'm storing 1 by 2m so that I don't have to calculate it multiple times. Although it won't be a big problem if I actually do it. Then yeah, so this is the column vector, the that came from the input. Just this array, I made it like a column. So yeah, this is the column vector, and now I am building the matrix. So obviously for the diagonal elements, matrix of I comma I equals 2m minus di divided by 2m. So yeah, just this thing. And while taking the edges as input, I'm keeping a count of the degree of all the vertices. And yeah, so mx and matrix xy and matrix yx becomes 1 by 2m. And yeah, the answer is just matrix to power k multiplied with the column vector. That gives us the answer. And yeah, so yeah, that's how we can do this. And the contest is about to finish. And thank you for watching. Remember to subscribe to my channel and see you next time.